right, good evening, everybody. Welcome to the 15th lecture in our series on history and philosophy of science and 20 objects. This evening marks the three-quarters way point. We have what we think is a pretty interesting object for you, but also a pretty interesting subject. Our object is the Barr-Stroud Rangefinder. You see that here. This is a bit of advanced optical weaponry from the decades around 1900. It was invented here at the University of Leeds, and it was used on battlefields in order to increase the accuracy with which a gunner could hit a target at a great distance. Our subject is something considerably grander than that, though. Our subject is the science of light, optics, used as a case study for understanding the relationship between two important kinds of success in science. One you might call theoretical success, when someone has an idea which just seems to work, classically in science, by generating a novel prediction which turns out to be true. This has always been impressive. It was impressive in the 18th century when, as Edmund Halley predicted, the comet that was seen in 1682 came back again in 1758, 1759, just as Newtonian mechanics said that it would. It was taken to be an immense vindication of the truth of Newton's principles. In the 19th century, Darwinian theory predicted that there would be found in the rocks a form which was more closely intermediate between humans and the apes than any that had been found before. And in the 1890s, in Java, as it then was, Indonesia as it is now today, it was found. Java man, it was known. We know it as Homo erectus. Again, a prediction borne out. The 20th century, we're spoiled for choice, but you might think of the way that Einstein's theory of general relativity generated predictions of black holes, and lo, there are black holes. It's very impressive when predictions work out. We tend, as a tribe, to think, tick, there is something to this theory. So that's one kind of success in science, theoretical success. Another, interestingly different and yet interestingly related kind, we could call technological success. Often these are the things that become the symbols of science and what it's done for us. Maybe nowadays it's your iPhone, the immense computing power we all carry in our pockets now. Endless astonishment. And it is. It's an astonishing device. And as you go back down the decades, there will be a different device which leads people to express awe and wonder at the times they're living in. Half a century ago, it was the Apollo space rocket. We still talk about this. If they can put a man in the moon, why can't they fix the traffic in Leeds? Why can't they make a printer that works properly? Whatever it is, we still talk. This is still a symbol for human ingenuity at its best. Go back another half century, here in Leeds, Louis Leprince takes a film of the bridge, cinema, phonography, the radio, wonders, everflow from the sciences in the form of new technologies. We've become accustomed to it. We're awed by it. We're disturbed by it. It's a feature of the modern world. It's a different world because these things continue to come. One shouldn't just focus on gadgets either. Think for a moment about medicine. In the mid-1980s, when HIV/AIDS came along, it was a death sentence. The other week it was announced that now to have an HIV infection is to have a normal life expectancy. It's absolutely astonishing, the kinds of progress made all over. And one of the things we ought to do within the history and philosophy of science is to ask about all of that. So we have theoretical success, we have technological success, and at least since the long 17th century, the era of the scientific revolution, we have some kind of a presumption of an important relationship between the two. Some sort of a relationship between getting the world right and becoming ever more successful at mastering the world, at controlling it. And the great propagandist for this view, of course, is Francis Bacon. Knowledge is power. Understand the world as it really is. Really sweat it. And at the end of it, you will have far greater power over the world than you would have had otherwise. That's the nature of the connection, says Bacon, between understanding and control. You could call that the Baconian Promise. And to my mind, no one ever put it better than a one-time Leeds MP, Thomas Macaulay, 19th century wonderkind, politician, man of letters, who wrote an essay on Bacon in which he sung the praises of science. And it's astonishing to think that this was written in 1837. This is what Macaulay had to say about science. It has lengthened life. It has mitigated pain. It has extinguished diseases. It has increased the fertility of the soil. It has given new securities to the mariner. It has furnished new arms to the warrior. It has spanned great rivers and estuaries with bridges of form unknown to our fathers. It has guided the thunderbolt innocuously from the heaven to earth. It has lighted up the night with the splendor of the day. It has extended the range of human vision. It has multiplied the power of human muscles. It has accelerated motion. It has annihilated distance. It has facilitated correspondence, all friendly offices, all dispatch of business. It has enabled man to descend the depths of the sea, to soar into the air, to penetrate securely into the noxious recesses of the earth, to traverse the land in cars which whirl along without horses, to cross the ocean in ships which run 10 knots an hour against the wind. These are but a part of its fruits and of its first fruits, for it is a philosophy which never rests, which has never attained, which is never perfect. Its law is progress. Now, what we want to do this evening is to apply a little historical and philosophical pressure to the Baconian Promise. It's going to be a lecture in 3 parts, and indeed we have 3 lectures for you. The first part of the lecture is going to be focused on theoretical success in optics. It'll be given by Juha Saatsi, associate professor here in HPS at Leeds, and he's going to take the story right up into the era of the Barr and Stroud Rangefinder. We'll then turn to consider the technological success side of the story. There, our lecturer will be Kiara White, a former master's student here, still working at the university and still our in-house expert on this instrument. We're delighted to have her with us. And then I'm going to come back at the very end to try to sketch in a couple of very general perspectives for thinking about this puzzling problem of the relationship between these 2 kinds of success in science. So that's where we're going. For now, if you would please join me in welcoming first Juha and then Kiara.
Okay, thank you, Greg. So before I let Kiara talk about the object, so what we have here is a product of very basic applied optics. Before Kiara talks about this, let me say a few words about the history of optics, just to set the context for the science of light that is behind the technological success that we have here. And I want to do all this in relation to a single philosophical question that I'm personally very, very interested in. And it's the question of scientific knowledge, its nature and extent. And in relation to light, we can ask more specifically, exactly what do we know about the nature of light? So keep that question in mind throughout my 15 minutes of talk. Now, of course, nowadays, you want to ask this question, what do? You Google it. You Google nature of light. And what you get is no less than 55 million and some results in 1.28 seconds, saying that light is a transverse electromagnetic wave that can be seen by humans. The wave nature of light was first illustrated through experiments on diffraction and interference. And like all electromagnetic waves, light can travel through a vacuum. Okay, sounds about right. Now, this may seem a little bit pedantic, but one could argue that there's a mistake here. Can anyone spot that? Well, the mistake I want to focus in is this first sentence here, which says that light can be seen by humans. Well, strictly speaking, one could argue that light cannot be seen by humans. What we see are objects that are lit or illuminated by light. We don't see light by itself. You can have a very strong laser beam traveling by you in a vacuum and you won't see it. It's only light that's scattered and is hitting your retina that you can see, that you can sense. Now, this may seem like a kind of point that only a philosopher would make, but it's a point worth making, because if you don't keep that point in mind, you can't really appreciate the kind of significant achievements that very clever people have made in theorizing about light from early Greek philosophers onwards. So we can start with Euclid of Alexandria, better known for his work on mathematics and geometry in his Elements. He also came up with a nice theory of light, the first geometrical theory of ray optics. Now, Euclid's theory was really a theory about direct vision, or something that you could say a theory of linear perspective. It didn't deal with light hitting intermediate bodies and reflecting or refracting from them, but rather getting straight from the object to your eyes, or the other way around. The first person that we know of who really thought about or theorized about the nature of light, how it reflects and refracts from intermediate bodies, was Claudius Ptolemy, better known for his astronomical ideas. Now, Ptolemy had a theory, geometrical theory of optics, which dealt with the laws that govern reflection and to some extent also refraction. It's bending of light when light hits the interface of two different media. Now, if you want to go beyond what Ptolemy achieved regarding refraction, you have to fast forward some 1,500 years all the way to, so these are some of the, these are some of the angles for which Ptolemy discovered laws of refraction. It's a limited set. If you fast forward some 1,500 years to early 17th century, you get Snell discovering Snell's law empirically, this beautiful quantification of how the bending, how the angles, the bending of light when light hits the interface of two media, how it depends in a very straightforward way on the speed of light in those two media. Broadly known as Snell's law. The French like to call it Descartes' law. There's a bit of a dispute about the ownership over this law. The French think that Descartes got it first. Now, as far as science of light is concerned, that's pretty much all you need to understand the operation of the object we have here this evening. As I said, it's a product of very basic applied optics. All you have is reflection and refraction by the lens and the prism there. That's all that's going on. So as far as the science of light is concerned, the object is in many ways very basic. But let's think about this philosophical question that I put to you. What do we know about the nature of light? As I said, it's very important to keep in mind the following things about light when thinking about this question. Light is in and of itself unobservable. It's not something that you can directly see by the naked eye. Therefore, the kind of knowledge that we have about light is more or less theory-mediated. What we have is a theory about light, what light is, and that theory is then supported by data. There's evidence for the theory. To believe the theory, take it seriously. What is evidence? It's a good question. At some level of abstraction, you can say that evidence is a matter of the theory explaining the data, providing a nice unified account of different optical phenomena, capturing the regularities that we call data. Now, appreciating this idea that our knowledge of the nature of light is theory-mediated, or theoretical in this way, is very important if you want to really think about this question. What do we know about the nature of light? Only then you can understand how, in the past, very clever people have had some very odd ideas about light is, what the nature of light is. So the early Greek philosophers of nature, who discovered these basic regularities of how light reflects and refracts and how it travels in straight lines, thought, for example, that light is something that is emitted by the eyes, and so the very direction of light is something they got wrong. So the ideas about the very nature of light by the modern lights was totally misguided. Now, Google, of course, spits out the contemporary answer very conveniently. As we said, light is what Maxwell's electromagnetic theory tells us it is. Here's one hit that comes up. What is light? Since the time of Young and Fresnel, we know that it's a wave motion. We know the velocity of the waves. We know their lengths, and we know that they're transverse. In short, our knowledge of the geometrical conditions of the motion is complete. A doubt about these things is no longer possible. A refutation of these views is inconceivable to the physicist. The wave theory of light is, from the point of view of human beings, certainty. Why so certain? The answer is obvious. The evidence is so good. The evidence for Maxwellian electromagnetic theory, which is the framework that underlies our current understanding of optics, is superb. It's absolutely fantastic. But for a historically minded philosopher, it's good to think about these theories of light in a less myopic way. Look back and look at the different theories of light, the different ideas that very clever people have had about the nature of light, and see how those have changed radically at the same time as there's been a natural accumulation of knowledge, of the sort of knowledge that underwrites, for example, the application of the object today. An eminent philosopher of science from the LSE, John Worrell, lovely turn of phrase captured to this idea that when you look at the history of optics, you see these ideas about the nature of light going from chalk to cheese to superchalk. Chalk being this idea that the early Greek philosophers of nature had about light being a matter of a stream of atoms traveling across space. For them, it traveled from eyes to the object. Then, if you go to the 17th, 18th centuries, certainly 18th and 19th centuries, people thought that light is a wave motion. The waving of what? The ether, of course. This kind of elastic solid that is meant to pervade all of the universe, is incompressible, and the waving of which amounts to light. That's cheese. And then, of course, nowadays, we've gone back to some extent to a particle conception of light, given that we know that the electromagnetic field is quantized, the quanta of which are photons, the particles of light, and the wave nature of which is then understood in quantum mechanical terms or quantum field theoretical terms. Now, in the Victorian era, in the days of Barr and Stroud, cheese dominated the day. So let me give you some quotes just to give a flavor of the kind of commitment that the leading scientists of the day had towards this wave conception of light, this idea that light is a waving of the ether. So here's, for example, Hermann from Helmholtz, a leading German physicist, saying that there can be no longer any doubt that light waves consist of electric vibrations in the all-pervading ether, and that the latter possesses the property of insulator and magnetic medium. William Thomson, later Lord Kelvin, contemporary Scottish physicist, made important contributions to mathematical treatment of electricity and magnetism. You can imagine particles of something, the thing whose motion constitutes light. This thing we call the luminiferous ether, and that is the only substance we are confident of in dynamics. One thing we are sure of, and that is the reality and substantiality of the luminiferous ether. One more. Here's James Clerk Maxwell himself, the unifier of electricity and magnetism, the creator of the theory that's really the foundation in many ways of our current understanding of light. Whatever difficulties we may have in forming a consistent idea of the constitution, the physical nature of the ether, there can be no doubt that the interplanetary and interstellar spaces are not empty, but are occupied by a material substance or body, which is certainly the largest and probably the most uniform body which we have any knowledge. Why so certain of the existence of this kind of luminiferous ether in the late 19th century? Because the evidence was taken to be so good. Why was the evidence taken to be so good? Well, to cut a long story short, these ideas about the ether are best explained, they're best unified, they best captured the data regarding different optical phenomena. There's a lot to be said here about the specifics, exactly what this goodness of evidence boils down to. Let me just give you one little glimpse of this in relation to one of these theoretical successes that Craig alluded to in the introduction. Now, remember that when you have light hitting the interface of two media, it can reflect and it can refract or bend into that denser medium, or, as often happens, it does both. Now here's a question. In what proportion does light reflect, and in what proportion does it go through into the material? Fresnel, Augustin Fresnel, a leading French physicist of the early 19th century, derived his so-called Fresnel's equations that are still known today that exactly capture the proportional intensities of light that are reflected and refracted. He derived that equation from ideas about the physical nature of the ether. That's the kind of theoretical success that gave the confidence to ether theorists that ether is a real thing. Okay. Before I hand over to Kiara to talk about the object and the history of it, I'm just going to leave you with a couple of questions which think on the way home. What did the Victorians know, if you think of Barr and Stroud, the creators of this object in the late 19th century? What did they know about the nature of light, given the best science of the day? A more difficult question, what do we know of the nature of light, given our best scientific theories of today? Is there any reason to take what Google spits out with a pinch of salt, or not? Okay, I'll leave you with that, and Kiara, you have the floor.
Thank you, Juha. So, as you've heard, the instrument that inspired tonight's lecture is the Barr and Stroud Rangefinder, which we have on display here. So put simply, as the name suggests, a rangefinder is just an instrument for accurately determining a distance. So a key use for these instruments was the military. And what they used them for was to check the distance of a target object. So for example, an enemy ship before firing. And they would also use it to check how much the range would change during firing. And the reason they needed to know this was so that they could set the elevation of the gun barrels correctly. Because if they were set too high, the curved trajectory followed by the projectile would overshoot the target object, or if they were set too low, it would fall short. So we can actually use our binocular vision to determine short distances quite accurately if we've been trained. But this is inadequate for the longer distances involved in war. So as technology advanced, the gunnery ranges increased, and the need for accurate rangefinders became even greater. So how do they work? Well, most rangefinders work by measuring the angle of convergence created by the two lines of sight from each end of the rangefinder. So in our diagram here, T is the target object, and PT and ST are the two lines of sight from the rangefinder. And where they converge, we get the angle of convergence. And this is determined by two things. One is the range of the object, and the other is the length of the rangefinder. So as the length of the rangefinder is constant and known, any size angle will have a corresponding range for that rangefinder. So this can be calculated in advance and displayed on a pre-calibrated scale. So if you look at the angle TSI on the right-hand side, that is equal to the angle of convergence, and that is actually what the rangefinder would measure to work out the range of the object. So we'll talk more about how these instruments work later, but first I want to introduce you to these two people, and they are Archibald Barr on the left and William Stroud on the right. So Barr arrived in Leeds in 1884 to teach engineering, and Stroud the following year to teach physics. So this was prior to the founding of the University of Leeds, and it was actually at the Yorkshire College of Science that they taught. So the Yorkshire College was established in 1874, and it aimed to provide students with an industrially relevant scientific education. And part of the motivation for this was to make sure that students could keep up with the fast-paced technological changes of the Victorian era. So there was concerns that, for example, the local cloth trade would be threatened by the new technological advances in the wool and textile industries. So as it was supported by local industrialists, the college, and on the left of the picture you might recognize Clothworkers Court, and this just under the arch there, and this housed the Textile Industries Department, which was built and equipped with funding from the Clothworkers Company. It was in 1904 that the university was given a royal charter to become a university. So when Barr and Stroud arrived, they were both very disappointed with the teaching equipment that was available to them. So Barr actually described it as consisting of nothing more than a chair, a blackboard, some chalk, and a chair without a seat. No laboratory was the key fact. And it wasn't actually uncommon at this time for universities and colleges in Britain to be insufficiently equipped to practically teach the principles of engineering. But they were both determined that their lectures should involve experimentation. But the Yorkshire College lacked the funds to pay for the facilities that Barr wanted. So what he did was he went around local industrialists and asked them to help fund new facilities. And he would have emphasized to them the importance of a practical education and the benefits that graduates who had received such an education could offer as employees. And he was able to raise £10,000, which he used to build a state-of-the-art laboratory. Now, Stroud also wanted to include practical demonstration in his lectures and likewise lacked the available facilities. But sadly, he had less success in raising money to pay for the facilities he wanted. So what he actually did was, so he would spend a long time writing descriptions of how the experiments would have been carried out if they had the equipment available. And he also produced diagrams on black cloth to illustrate the lectures. And obviously this took him a long time, so one thing that he did was work with his assistant and designed a magic lantern, which we actually have on display here. So this is called the science lantern. So magic lanterns are early forms of projectors, and they're often used for entertainment, but also for educational purposes. And this one here has a modification that allowed a scientific experiment to be carried out in this space here, and that would be projected for all of the students to see. So it was this task of illustrating lectures that drove Barr and Stroud's first collaboration. So they produced a lantern slide camera, and what this did was it allowed you to easily produce lantern slides made out of glass from any textbook illustration or sketch or photographic print, or actually any flat objects. That could even be something like a botanical specimen. Unfortunately, we don't have one of these cameras in the collection, but we do know that it was manufactured by W.M. Middlemiss in Bradford, and they also patented it in 1889, and it was used in universities around Britain. However, this isn't the invention that they would most be remembered for. So in the May 25th, 1888 article of Engineering magazine, the War Office had placed an advert requesting inventors to submit designs for a new military rangefinder, and the submitted designs would be entered into a competition. So there was an instrument in use at the time called the Watkins micrometer, and this was fairly accurate in good conditions, but it had some key disadvantages in the field environment. So it consisted of a cord of 25 to 30 yards in length, and at one end there was an optical square, and at the other end there was a box sextant. and each was held by an observer. So one observer held the optical square and stood at a right angle between the line of sight to the object in question and the other observer. And the second observer would use the box sextant to measure the base angle and read the range from a scale on his instrument. But the problem with this instrument in a field environment is that it had delicate optical parts and calibration, which could be easily damaged. It also required two observers, and of course they were about 30 yards apart, which meant they struggled to communicate with each other and also with the gunfighters, and it could take them up to 5 minutes to read a range, which was far too slow if the ship was advancing quickly. And this was putting lives at risk, and it also wasted a lot of ammunition. So this is what inspired the War Office to place the advert in Engineering magazine. So there was a list of requirements that the new design needed to meet. So it should accurately measure ranges up to 2,500 yards with a margin of error of no more than 100 yards. So it had to be very accurate. It should display the range without further calculation. It had to withstand poor weather and rough conditions so that a soldier could carry it along with his rifle without it getting damaged. And ideally, it would be operable by just one person, but definitely no more than two. So the morning after this advert appeared, Barr went to visit Stroud and suggested that they started work on a design to submit. And Stroud agreed, and they set to work. So what they needed was an instrument that was as accurate as the kind of instruments they would have been used to using in the lab, but that had the durability to survive at sea or in the field. So you would think that their combination of expertise in engineering and physics should make them well suited to this task. However, they hadn't worked on rangefinders before, and it wasn't an easy ride. There and then, we decided to enter the competition for rangefinders, about which neither of us knew anything. In blissful ignorance of what had happened, what had already been done on the subject, we dashed off regardlessly. The first rough instrument we made was a ghastly failure. So their design was submitted to the War Office by the deadline of the 1st of August 1888, and the next month they found out that they had successfully passed the first stage. So they now had 4 months to produce a prototype instrument and submit it to the War Office by the 1st of January 1889. So let's now take a bit more of a closer look about how this particular model worked. So at each end of the object there is windows for light from the target object to enter the instrument. And then the light that enters is reflected by reflectors or prisms towards the center of the object, where there's an eyepiece through which the observer would view 2 images of the target object. So this type of rangefinder is called a coincidence rangefinder, and this is as an example of the view that you might see when looking through the eyepiece. So here you can see the target object is a ship, and if you look at the mast, you will see that it's not aligned. So what the observer would do is turn a wheel on the instrument, and this would move a refracting prism along the path of the right-hand beam of light, and this would cause the images to be displaced relative to one another. So they would keep turning until the images were aligned, or in coincidence, hence the name. And the amount that they needed to turn the wheel depended on the inclination of the beams of light, which in turn depended on the distance of the object. So when they were in coincidence, this is called taking a cut, and they could then read the range from a pre-calibrated scale. So their design went to the trials, which took place in Aldershot during March 1888, and theirs was the only single observer instrument to be invited back for the second round. And if you'll recall, being a single observer instrument was one of the things that the War Office wanted. However, in between the first and the second trials, Barr and Stroud were quite concerned because their object was more expensive than a lot of the other instruments in the competition. So what they did was they took the glass prisms at each end of the object and replaced them with cheaper silvered reflector mirrors. So they went along to these second trials, and in the morning their modified instrument performed quite well. But in the afternoon the clouds cleared and it got quite sunny, and the heat from the sun actually distorted these mirrors that they'd put in. So across the afternoon, the readings of their instrument became increasingly inaccurate. So unsurprisingly, they found out that their design was rejected as unsuitable for military use. However, they did learn a lesson from this. They learned never to sacrifice design and performance for cost. And the design had showed promise. So actually, in 1891, they were approached by the Admiralty and asked to submit a design for a naval rangefinder in 1891. Now, by this time, Barr was actually working in Glasgow. He was a chair of engineering at the university there. But they had continued their collaboration. And although this distance might have caused some difficulties, the biggest problem for them was actually financial. So as with the first instrument, they weren't offered any financial help from the War Office to produce their prototype design. And Barr recalled that money had to be raised and saved at all costs. And what Stroud did was he went round local towns and villages around Leeds and actually gave entertainment lectures using his magic lantern and slides. And I think he was paid £3 for each lecture. And they used that money to help them help them build their prototype. So this new model was trialled on HMS Arethusa in 1892. And this time, they were able to satisfy the accuracy and stability requirements, and they did win the competition. So their naval rangefinder was adopted by the military after these trials, and in 1911, their field rangefinder, which is what we have on display here today, it had been modified, and that was adopted by the Army. So soon, orders were received from all around the world, and Stroud later recalled that naval and military attaches crowded like wasps around an open honeypot to study the instrument, and orders quickly followed. So they established their company, Barr and Stroud Patents, in 1894, and all they had at that time was a small workshop over the Barrows Road subway in Glasgow. But as their orders increased and their designs became more complex, they had more staff, and they also produced a wider range of instruments, they required more purpose-built space. So they purchased some land at Annie's Land in the northwest of Glasgow, and they built a 1-storey workshop and a 3-storey office building. And the size of this factory increased over the years. In 1912, they became a private limited company called Barr and Stroud Limited, and they manufactured thousands of rangefinders in the run-up to World War I and 30,000 for World War II. And during peacetime, they also diversified into more civilian products, such as film projectors and binoculars. So in 1977, they merged with the Thales Group. They merged with Pilkington, which is a subsidiary of the Thales Group, and actually still exists today. But the Barr and Stroud name was sold to another company who sold optical instruments, such as binoculars or magnifying glasses. So one of the reasons why they were so successful was that they could produce high-quality instruments that met a market demand. But I think there are two other key features that we can identify that led to this success. And the first is that they were aware of the importance of protecting their intellectual property. And the second is that they had a very strong commitment to scientific education, as we heard earlier, and also linking science and industry closely. So they displayed a recognition of the importance of patent protection even before they set up their firm. So before submitting their design to the War Office, Barr wrote to them and asked them a few questions concerning the intellectual property. So he asked, will the invention selected become the property of Her Majesty's government, or will the inventor be at liberty to trade with foreign government with a view to its adoption by them? And finally, will it be necessary or advisable to obtain provisional protection for the invention before it is submitted for trial? So you can see that they were concerned about what they would be able to get out of this instrument that they had made. Would they be able to profit from it? So the War Office advised them that the intellectual ownership and any restrictions on trade, they would really just depend on any agreement made after trial. And whether or not they should get patent protection from it, well, that was up to the inventors, really. But Barr and Stroud did decide to take out a patent for their object, and it looks like they originally planned to just sell the rights to this patent but they valued it at £75,000, and the War Office thought that was too expensive, but instead of lowering their price, that's why they decided to set up their company. They weren't going to sell it for less than they valued it at. So it was crucial that they secured the patent at this time. So a patent grants the inventor permission to stop other people from manufacturing similar instruments for a limited time period. And the German firm Zeiss had actually been working on a very similar coincidence rangefinder at this time. But because Barr and Stroud's patent prevented them from manufacturing this, they decided to work on stereoscopic rangefinders instead. And stereoscopic rangefinders, instead of seeing those two images that you have to bring into coincidence, you see the image with a series of black arrows, and you have to judge which arrow lies closest in depth to the object. And so this requires more training than Barr and Stroud's instrument, and it also requires equally good vision in both eyes, whereas Barr and Stroud's, you can use it even if you only have good vision in one eye. And stereoscopic rangefinders, you also need to be able to control the sensitive muscles in your eye very well. So even in people who do have this ability, it can be impaired by ill health or mental strain, such as the psychological pressure that you might experience during the war. So it had been noticed, actually, that the accuracy of German gunnery would decrease after their ships had been hit. And it was actually reported that during the Battle of Jutland, all of the range takers on 2 German ships were incapable of stereoscopically determining the range after their ship had been hit. So obviously, the ability to manufacture coincidence rangefinders put Barr and Stroud in a good position in the eyes of the military. So their original patent expired in 1907, but that left them open to competition from other companies producing a coincidence rangefinder, so they were determined not to lose their protection. So what they did was they designed and patented 2 additional features to make the instrument more user-friendly. So they added a combination of prisms inside the rangefinder, which allowed the eyepiece to sit at a 45-degree angle, which was the most comfortable angle for the range taker. It reduced neck strain. And they also added 2 fold-away carry handles, which you'll be able to see if you look at the back of our instrument after the lecture. But Zeiss and Goertz is another German firm, they both challenged these patents in 1911. They claimed that they weren't based on scientifically important inventions or improvements. So what Barr and Stroud did was they entered negotiations with these firms, and they convinced Zeiss to drop the challenges by giving them exclusive rights to these features for rangefinders destined for the German authorities. But Goertz continued their challenge and did actually overturn the patents, but Barr and Stroud were able to successfully appeal this decision. So this allowed them to keep their intellectual property protection and, in turn, retain their market dominance. So we'll now look at the second feature of their success, and this is the linking of science and industry and pushing for a high-quality, practical scientific education. So Barr had felt that the education system at the time wasn't sufficiently preparing students to work in industry. As he said, the teacher and the research student should both be in intimate contact with the requirements of the industry to which their work has reference. And likewise, those who are working in industry should have a thorough understanding of the scientific principles that ground the work they are doing. Barr stated that scientifically trained employees are indispensable for the development of work in new lines, and we seldom, I may say never, appoint a man to a responsible job, even in the supervision of purely workshop work, who has not had a sound and extensive course of scientific training. And he had expressed a similar sentiment earlier in a lecture he gave at the Yorkshire College in 1888, and this was titled The Engineer of the Future. So he said that it is crucial that the scientific basis of practice should be known and understood to all those who have to direct this practice. To have a firm grasp of his work, the engineer must know not only, for instance, that an engine gives such and such results, but why it gives them. Otherwise, they would not be able to work out what is and isn't possible, nor the reasons for their success and their failures. All they would be doing is groping their way by hard lessons of failure and chance runs of luck. Now, this might not sound very controversial, the idea that it's useful to know the scientific principles behind the work you're doing. But let's compare it to this quote from The Engineer magazine, which appeared later that same year as Barr gave the lecture. And this says, "At the root of all this worry about technical education lies the delusion that unless men are taught certain things, they cannot produce steam engines or cotton cloth or iron, the fact being that a knowledge of the things in question is wholly unnecessary. So that's a very strong contrast to Barr's sentiment. And actually, you know, this was common at the time, this kind of neglect of technical and scientific education in Britain. And it was linked to the ideal, the traditional ideal of a liberal education, which would involve a focus on subjects such as classics, mathematics, and philosophy. And this tradition was expressed by John Stuart Mill in 1867 when he said, "Universities are not intended to teach the knowledge required to fit men for some special mode of gaining a livelihood." So, you know, we shouldn't have vocational education. That's not what a university is for. And it was the founding of institutions such as the Yorkshire College was partly in response to this situation. They taught more scientifically relevant industrial subjects, as we heard earlier. So this went some way to changing the picture that we've just heard about. However, Barr and Stroud did still feel the effects of this tradition. So they struggled to find employees for their company who met the high standards of education that they had. So one thing that they did was turn to the University of Glasgow. So we heard that Barr had worked there, and while he was there, he had significantly improved the teaching facilities in the engineering department. And they also set up a 5-year apprenticeship program within the company, and that allowed employees to attend science classes in the evening, and they also encouraged the best ones to go to university. And another way in which this inadequate technical education manifested was with the supply of optical glass. So optical glass was used, obviously, to produce instruments such as the rangefinder, and it had to have a high level of surface accuracy. So producing this glass is very skilled work, and there was a shortage of people who had the education appropriate to allow them to make this glass. So companies such as Barr and Stroud had to turn to foreign suppliers. So for example, in 1914, just before the outbreak of the war, 60% of optical glass used in the UK was actually obtained from Germany. And in Germany, firms such as Zeiss, who was mentioned earlier, they had some control over the curriculum in local technical schools, and attending such a school was actually a prerequisite. It was a requirement of entering a trade. So this source of optical glass from Germany, this ceased when the war began, leaving them in quite a predicament. And Barr and Stroud actually ended up establishing their very own glass works and training up their own employees, and within 9 months they were able to produce glass of an appropriate standard to use in instruments such as the rangefinder. So I'm now going to hand back to Greg, who's going to have a look at some of the themes emerging from the history of Barr and Stroud.
Thank you, Kiara. So in our subtitle for our lecture this evening, we promised you a lecture on the magic and the mayhem of optics. With Juha, you got something of the magic. Fresnel, with what we now regard as false ideas about the nature of light, nevertheless deriving equations which still work. There's something magical about that. With Kiara, we turn to the mayhem of optics. People died on land and at sea because Barr and Stroud successfully built their rangefinder. I now want very briefly at the end to sketch in a couple of larger perspectives that the history and philosophy of science give us for thinking about the relationship between theoretical success and technological success. And I want to begin by saying that this is a really hard problem, and I don't think our field can hold its head up high in its ability to make any headway with it. It's very difficult to do justice to the nature of the problem. Neither of the perspectives I'm going to share with you now quite do the job, but I find them inspiring company, and you might as well. Both derive from figures who have been mentioned in these lectures previously. This is Robert Merton. You might remember him in connection with the Newland-Phillips machine. He gave us the phrase self-fulfilling prophecy, as well as a number of other linguistic innovations. But what I have in mind today is an insight of Merton's into the very beginnings of modern science, that long 17th century, the period of the scientific revolution. What he noticed is that a couple of things begin in this period, a couple of kinds of fights. There are, first of all, priority disputes. Disputes about who got there first. That doesn't happen, Merton says, during the medieval period. During the medieval period, when one has something new to say, one on the whole represents it as something coming out of Aristotle, coming out of antiquity. In the early modern period, by contrast, one says this is new and different. It goes beyond where antiquity left us. It's also the period in which you get the first patents. And with the first patents come the first patent disputes. And again, novelty here seems to have a kind of valuation that it didn't have during the medieval period. And if we review the material we've covered so far in the lecture, we'll recall that priority disputes came up briefly in Juha's part of the lecture, where we learned that Snell's law is known in France as Descartes' law. It matters to scientists that they get recognized for being first. Indeed, on Merton's larger sociology of science, that economy of crediting priority is part of the engine of science. The willingness of people to share their discoveries depends on their trust in the system to acknowledge them properly. And that acknowledgement often comes in the form of a name on a law or a set of equations. Moving to Kiara's lecture, patents came up. Barr and Stroud were able to do what they did because they looked after the protection of their innovations. And those also were contested. So we have two kinds of ownership being claimed here. Ownership of a piece of theoretical knowledge in the form of a priority claim. Ownership of a piece of technological innovation in the case of a patent claim. You might also, though this might be a bit of a stretch, see a kind of an ownership grab here in the claim that Barr made that if you really want productive engineers, they have to be scientifically trained. Optical knowledge comes to have a kind of ownership over optical technology. If you want to be successful in your technologies, you have to understand. And again, as we saw, that's contested. So you might even try to generalize Merton's insight from the 1930s in this sort of a way, to think about priority claims and patent claims and productivity claims, as you could call them, those claims that bodies of knowledge are themselves productive technologically, as somehow important and interacting as we try to understand quite what it is that's made science so technologically inventive, and quite why it is that scientific knowledge has the authority that it has, and the links between the technological success and the authority. As I say, all of that is just a sketch and a start, but it's at least that much. Alongside Merton, I find, in a complementary way, Ian Hacking, Stimulating Company. Hacking lectured here. He came up in a previous lecture, in Juha Saatsi's lecture, about the microscope. But what I have in mind this evening is an essay that he wrote about the relationship between knowledge and weaponry. And what Hacking says is that throughout most of the history of science, this relationship had been one way. People find stuff out, and they make new weapons. But at a certain moment, the relationship became reciprocal. The new weapons fed back on the kinds of knowledge that got found out. And he dates that to the Second World War. Now, if we cast our minds back to our lecture, this kind of works out. We saw that the Barr and Stroud rangefinder depends not on 19th century optics, but on 17th century optics. The knowledge flowed one way. But if we want to think about the post-war period, we could think about the bomb, but Hacking says the bomb is just sort of too big. We can't get our heads around it. It's a little too exotic. Why not think, says Hacking, about lasers? We don't think often enough about lasers as having derived from the Second World War. But they do. There's a line to be traced from radar, the use of radio pulses for detection, through the maser, onto the laser. Maser stands for microwave amplification by stimulated emission of radiation. But it was joked at the time that it was better known as the means for acquiring support for expensive research. Because after the bomb, the word is out that if you want your nation to succeed among other nations in having the advanced weaponry and staying secure economically as well as militarily, you have to fund your scientists and you have to fund them to the hilt. And this worked out as well for the people working on lasers as well as on nuclear technologies and many other things. Nowadays, of course, if you want to get a rangefinder, it's a laser rangefinder. So this notion of a reciprocal relationship is, I think, one worth thinking about. What hacking's suggesting is that with laser technology, it's not just that lasers become part of our domestic world, in our printers and our CD players, not just that they become useful to the military for anti-ballistic missile defense. They also enter the laboratory. And because they enter the laboratory, they change what gets found out. They ask the kinds of questions people want to pose. And parenthetically, the kinds of questions that don't get posed. And we need to think about that, hacking suggests. Again, that's, like Merton's perspective, just a sketch, just a start on the thinking that still needs to be done about the relationship between theoretical success and technological success, between the magic and the mayhem, not just for optics, but for science as a whole. Thank you very much.